Okay, so the last part of the course, you're going to be working with AC circuits. So this is more aligned with electrical engineering majors, although the information that is going to be presented is equally important for ECEs and for COEs. In other words, it's really basic electrical engineering material. Again, what I will be presenting is not the official material of the course. This is supplementary material. Yung official material has already been published sa UVLE. So take a look at that. Yan yung official. So kung ano man yung i-introduce ko rito, think of it as supplementary. No? Pampadagdag lang. But your main reference should be yung nasa UVLE. Okay, I'm going to start with a discussion of capacitors and inductors. So electrical characteristics of capacitors and inductors. So sa inyo, no, have you been exposed to capacitance and inductance before? May I have a show of hands? Or no? So may konting alam na rin kayo tungkol sa capacitance at saka inductance. Oh, good. So this is going to be some sort of review. So let's start with the capacitor. A capacitor is a circuit element consisting of two conducting surfaces separated by a non-conducting material called a dielectric. A dielectric is a fancy term for insulator. So it's two conducting surfaces separated by an insulator. And the capacitor has the ability to store energy within an electric field. So these are some images of the construction of capacitors. So here you see two conducting surface. You have two metal plates. And then in the middle of the two metal plates, you have an insulating dielectric. You call this a parallel plate capacitor. Most of the time, this is how we represent capacitance. But actually, it does not have to be parallel plates. For example, you can have a cylindrical capacitor. In this case, your two conducting surfaces are wound in the form of a coil. You have an inner conductor and an outer conductor, and you have a dielectric in between the two. Okay. On the other hand, in integrated circuits, you have this particular construction of your capacitor. Now, if you recall the MOS construction that I discussed with you, the metal oxide semiconductor construction, that is actually a capacitor. Now, you have a metal layer, okay? And then in between your metal layer and your semiconductor layer is a dielectric, which is silicon dioxide. And then here you have a semiconductor layer, which acts as your second conducting layer. So this is your MOS, your metal oxide semiconductor capacitor. And if you take a look, these are images of various types of capacitors. Some of these you've probably encountered in your high school laboratory days. Some you see in printed circuit boards. Okay, let me describe how a capacitor works. So this is your parallel plate capacitance. Okay, so let's use this to illustrate how a capacitor works. So you have a top plate and you have a bottom plate. Typically, these are conducting material or metal. And then you have your dielectric sandwiched in between. Your dielectric, by the way, does not have to be, it can be air or it can be a vacuum, as long as it is a non-conducting layer. And this is the circuit symbol for your capacitor. So the reason why we use this symbol is it sort of depicts two plates. No? So this is one plate and this is the other plate. Okay. And just like any other passive element, yung resistor is a passive element, just like any other passive element, if the current flowing through the capacitor is in this direction, then you encounter a potential drop in the direction of the current, meaning to say the charges transfer energy to the capacitor, no? So that when the charge comes out of the capacitor, it has less energy than when it entered. And therefore, you have a potential drop. No? So that's common with all passive elements. No? The resistors you're already introduced. No? Okay, what happens? What happens when you apply a voltage across a parallel plate capacitor? So that's what I'm going to try to illustrate now. So let's say this is my, sorry. Okay, so let's say this is my parallel plate. Okay, let me expand this. No, so let's say this is my parallel plates. Okay, that's one plate. Is another plate, and then this is my dielectric. So this is my insulator. What happens if I apply a voltage across my capacitor? So let's say this voltage is V. Okay. This is an insulator. So is current going to flow through your capacitor? Yes or no? No? What do you think? That is an insulator. Will charges flow through your capacitor? Common sense, hindi ba? Hindi. Right? Charge cannot flow through your insulator. So what happens when I connect my voltage source? Well, this is positive, right? This is positive. I have electrons that are here. I have electrons that are here. So those electrons will be attracted toward the positive end of my battery. No? So I'll have electrons that are pushed up. Okay. And then what happens here in my negative? No? The negative is going to repel electrons. No? By the way, no, if electrons are pushed up, this becomes negatively charged. This becomes negatively charged. Okay? Sorry. Baliktad, no? Erase, no? Okay, what happens, no? Electrons are pushed up, no? So for a short time, electrons will flow in this direction. Toward the positive. Okay? For a short time, no? For a short time. And because electrons flow there, this becomes positively charged. Kasi nawala yung electrons. Okay, on the other hand, dito, the negative terminal is going to repel electrons from here. It will repel electrons from here. So the electrons will tend to go up. No? And because the electrons went up, this will become negatively charged. That will become negatively charged. And what happens is an electric field will build up here. Now, when will the electric field stop building up? Electric field will stop building up when the potential is equal to V. When the potential across the capacitor is equal to V. That's a potential across the capacitor. And current will not flow anymore. So wala nang current na mag-flow. No? Current becomes zero. Okay, so again, to summarize, no, when you first connect the battery, you're going to get electrons that will flow in this direction momentarily. That corresponds to a current flowing in this direction, I. No? And as that current flows, an electric field builds up here. Okay, nagkakaroon ng difference in potential between this plate and this plate. No? Because you have an electric field, nagkakaroon ng potential difference between this plate and this plate. And when that potential difference equals V, your current will stop flowing. At that point, you have an electric field in your capacitor. So that when I remove the battery, kung tatanggalin ko yung baterya, my electric field will still be there. It will not disappear. Okay? And that is the concept of the charge being stored in your capacitor. So what is the charge that is stored in your capacitor? It is not really charge being stored inside the capacitor, but it is really the displaced charge. This is your displaced charge. Okay. So the capacitor will have a displaced charge, Q. And that Q will be proportional to V. And the constant of proportionality is equal to C. So Q is equal to CV, where C is what we now call your capacitance. Okay. So, does the capacitor store charge? That's a nice question. Everybody says yes, it stores charge. But there is no actual charge from the current that is being stored here. What happens is, because a current flowed momentarily, you have charges that are displaced. No? This ends up being positive and this ends up being negative. But if you take a look at the totality of the capacitor, the total charge is still zero. Walang net positive or walang net negative charge sa loob ng capacitor. Pag sinuma total mo yung charge dito sa loob ng capacitor, it's still zero. It is just that your positive charges aligned here and your negative charges aligned there. And that created an electric field. No? So this is displaced charge. And your displaced charge is proportional to your voltage. Okay? And the constant of proportionality is called your capacitance. So there's a question. Yeah, actually, you might think of it that way. No, it's not really charged per se, but your molecules aligned, no, or your charges aligned so that the positives are on one end and the negatives are on the other end. No, so that is your displaced charge. Okay? And again, no actual charge can flow through your dielectric because that is a dielectric. Kahit anong gawin mo, walang charge na magfo-flow diyan, no? So when you say you have a current flowing through a capacitor, it is because charges are being displaced. It is not because there are actual charges that are flowing through your dielectric. No, it is because your charges are being displaced. Okay? So that is the concept of your capacitor. Okay? So let's go back, no, to what I said. Q, that is the displaced charge, or what we sometimes refer to as the stored charge, is equal to CV. No? C is capacitance, the unit is farad. Okay? 1 farad is 1 coulomb per volt. 1 coulomb is our unit of charge, so 1 farad is 1 coulomb per volt. Now, since I, if you recall, no, module 1, I is equal to dq dt. Okay, if I get the derivative with respect to t of both sides of this equation, I'm going to get I is equal to C dV by dt. And this is the relationship between current and voltage in a capacitor. I is equal to C dV dt. Okay. When does a current flow? A current will flow only if the voltage across your capacitor is changing. So we only get a current I kung yung V nagbabago with respect to time. Kung ang V natin is DC, we don't get a current flowing. And that is what's happening here. No? That's what's happening here. This is DC. At steady state, you don't have any current flowing. It is only the instant that you connect the battery that current will flow, and that is to establish the electric field. But at steady state, you don't have any current flowing. No? So yun yung repercussion nitong, or yung implication nitong formula na to. Okay? So the current through a capacitor is proportional to the rate of change of the voltage across it. Okay? I is equal to C dV dt. Rearranging and integrating, we can get an expression for V. V is equal to 1 over C, the integral from minus infinity to t of I dt. No? So you learn this in calculus. No? Now we can split up this integral into two. No? We can split this up into the interval from minus infinity to 0 and from 0 to t. And so finally, your expression for V is V sub O plus 1 over C, the integral from 0 to t of I dt, where you say V sub O is the initial voltage across your capacitor. So a capacitor, the voltage across your capacitor is something that will depend on its initial, what we call its initial condition. No? If it's initially uncharged, then that's the initial voltage is 0, but your capacitor can initially be charged. Okay? So these are the fundamental characteristics of your capacitor. One more, no? Power. Power is equal to voltage times current. So voltage, current is equal to C dV dt. No? Remember, I is equal to C dV dt. And therefore, power is CV dV by dt. And if you get energy, energy is the integral of power. No? Energy is the area under the power curve. And if you substitute, for example, this into this is the expression you're going to get. Okay. Notice that the dt is going to cancel out. Okay, because you have CV dV dt by dt. The dt is going to cancel out. So you have the integral of CV dV, which is just 1/2 v squared. No? The integral of v dv is 1/2 v squared, or v squared over 2. So the energy, notice that the energy stored quote-unquote stored in a capacitor is only dependent on the voltage across the capacitor. It does not depend on time or past history. Kung ano man yung voltage at that particular instant in time, that's also the energy that is stored in the capacitor. Okay, are there any questions with respect to the capacitor? Okay, I like to make an analogy between a capacitor and the diameter of a water tank. No, that's an analogy that might help you imagine the concept of capacitance. So, for example, if I have a water tank, let's say this is a water tank. Sorry. Okay, yung height ng tubig sa water tank, okay? So this is the height. Okay? This is analogous to your voltage. Okay, the diameter of your water tank is analogous to your capacitance. Okay? And then the water that flows into the tank, so let's say we have a valve here. No? So there's a water flowing. This is analogous to your current. Okay? And the volume of water is analogous to charge. The volume of water is analogous to charge. No? What is charge? What is current? Current is the rate at which charges flow. Okay, so charges, if there's current, if there's water flow, meaning there's current, nadadagdagan yung total charge sa loob ng tangke. Right? Okay, if there is water flow, the height will change. If the height is not changing, that means your water flow is equal to 0. Right? So in a capacitor, what is I? I is equal to C dV by dt. If your voltage is not changing, then that means your water flow or your current is equal to 0. Kasi ibig sabihin nun, hindi nagbabago yung voltage natin or hindi nagbabago yung height natin. Right? Now, by how much does your height change with water flow? Kung malaki yung diameter mo, okay, for the same water flow, mabagal aakyat yung height. Kung maliit yung diameter mo, for the same water flow, mabilis aakyat yung height. So ganun din sa capacitance, no? If you have a capacitor, for the same current, the larger the capacitor, the slower your voltage will increase. If you have a small capacitor, the faster your voltage will increase, no? And your total charge or the volume of water is proportional to your height. Right? In a capacitor, the total charge is proportional to your capacitance. Dito, your volume of water is proportional to your height. No? In the water tank, no, that is a function of your diameter. Right? In a capacitor, that's a function of your capacitance. So that's something that you can use to imagine a capacitor. Okay, let's discuss your inductor. Your inductor is a circuit element that usually consists of a wire wound in the shape of a coil. And this has the ability to store energy within a magnetic field. And you learned this in physics. You learned the right-hand rule. If you have a current flowing in this direction, so this is a conductor, if you have a current flowing toward the right, then you're going to have a magnetic flux around that particular conductor that is this way. No? Yun yung right-hand rule natin. No? If your current is flowing this way, then you have a flux flowing this way, no? Again, no, pag ganyan, yung flux pag ganyan. Now, what happens if I decide to make this wire a coil? So, gaya dito, no? Itong wire na to, ginawa kong coil. I wound it this way. And you make it a tight coil so that there is no space in between your turns. No? If I make a current flow through the coil, ang magiging direction ng flux will be along the coil axis. No? So along the coil axis, yun yung flux. No? Of course, it will go through the air and go back in. No? But it will be concentrated dito sa axis nung coil, no? And the amount of flux that will flow is equal to the number of turns of the coil times phi, no? Where phi is the flux that would have flown if you only have a single wire, no? Because now you have many turns here, the flux is multiplied by the number of turns n. Okay? We say that n phi is the total flux linking the coil. And n phi, the total flux linking the coil, will be proportional to your current I. And the constant of proportionality is your inductance, L. Okay? L is your inductance. L is measured in henries, and 1 henry is equal to 1 Weber per amp. No? Weber is your magnetic flux. Weber is a measure of your magnetic flux. Okay, what does Faraday's law say? Faraday's law says that a time-changing flux induces a voltage across a coil. Anong ibig sabihin nun, no? If I had, for example, if I have a flux, let's say I have a flux here, no? Let's say this is a flux, phi. And phi is changing with time. If I put a coil here, okay, I'm going to get a voltage here, V. Okay. I'm going to get a voltage across the coil. Only if phi is changing with time. A time-changing flux induces a voltage across the coil. No? So this is created somehow by some other circuit. No, it has nothing to do with this coil. It's created by another circuit. I put a coil in the vicinity of this flux. If this flux is changing with time, I'm going to induce a voltage V. Let me erase this now. No? V is equal to the number of turns of the coil multiplied by the rate of change of the flux, dphi by dt. This is actually an expression of Faraday's law. N is the number of turns of the coil. But remember that N phi is equal to Li. No? We showed that earlier in the earlier slide. N phi, the total flux linkage is proportional to the current. The constant of proportionality is your inductance. Meaning to say, if I substitute this now, this expression for phi here, I'm going to get V is equal to L di by dt. The voltage across your coil is a function of the current that is flowing through the coil. Okay? Now, this assumes that this current flowing through the coil is what creates the flux that the coil experiences. So this is what you call self-inductance. Now, in the drawing I showed earlier, that is not self-inductance. No, that is, in other words, it's not the current flowing in the coil that produces the flux phi. But in this case, the current flowing through the coil, this current, if it is changing with time, will cause a flux to be created by L, which is also changing with time, that will induce a voltage across it, which is V. No? Okay, so if I manipulate this equation, I get di 1 over L V dt. I integrate, I get this expression. This is the expression for your current flowing through your inductance as a function of the voltage across it. And just like what we did with the capacitor, I can split this. I can split this integral into two. The integral from minus infinity to 0 and the integral from 0 to t. Okay, so I come up with this expression. And all this says is that the current that flows through your inductance depends on an initial condition. And that initial condition is the current flowing through your inductance at t equal to 0. Okay, this is how inductors might look like. So some of you may have seen seen inductors before. These are various types of coils. Okay, these are axial coils. These are toroidal. You call these toroidal coils. Okay, same thing we did with capacitance. Expression for P is equal to VI, but V is equal to L di dt. So you just get this expression for P. And if you want to get an expression for energy, you integrate P with time. So that's the integral of P dt. And you come up with this expression, energy is 1/2 Li squared. In other words, the energy stored in an inductor depends only on the current flowing through it. Okay, if you notice there seems to be a similarity between your capacitor and your inductor. Your capacitor is able to quote unquote store charge. Your inductor is able to quote unquote store flux, magnetic flux. Okay. Charge is stored in a capacitor when a sign that charge is being stored in a capacitor is your voltage changing, and a sign that flux is being created or depleted in an inductor is your current is changing. So there seems to be a dual relationship between, well, actually you call this duals, no? So this is the dual relationship of your capacitor and your inductor. Okay, so for your capacitor, I is equal to C dV dt. For your inductor, V is equal to L di dt. For your capacitor, this is your expression for voltage. For your inductor, this is your expression for current. For your capacitor, energy is equal to 1/2 CV squared. For your inductor, energy is equal to 1/2 Li squared. So the defining equations are identical if we interchange C with L and we interchange I with V. Now, the repercussions of these relationships, for a capacitor, your voltage cannot change instantaneously. And for an inductor, your current cannot change instantaneously. Why is that so? Okay, so let me make a very simple illustration. No? Let's say this is V versus T. Okay, let's say my voltage is like this. Okay, and I apply this voltage now to a capacitor. So plus or minus V. What will my current look like? What will my current look like? I versus T. Okay, what's our expression for I? Can somebody remind me? Ano yung expression natin for I? I is equal to what? C dv dt. C dv dt. What is dv dt here? Anong value ng dv dt dito? Anyone?
That's 0 po.
0, right? 0. So 0. No? What is dv dt here? Dito. What is the value of dv dt here?
0 din po.
Also 0. So yan ba yung itsura ng I natin? Yes or no?
Hindi dapat po.
Why not? Why not? Let's hear from si Justin ang sumagot, no? No. Why not, Justin? I know it's hard, no? Nag-change yung voltage natin, di ba? Nag-change, no? Initially, your voltage was 0. Ngayon, nagkaroon tayo ng voltage na V. Ano ibig sabihin nun? Ibig sabihin nun, nagkaroon ng charge yung capacitor. Okay? Nagkaroon ng charge. Kailan siya nagkaroon ng charge? I mean, when did current flow so that it charged the capacitor? Okay. If you take a look at this area, dv dt is equal to infinity. Dito, dv dt is equal to infinity. No? Because the voltage rises at time t equal to 0. So if you take a look at the slope of this line, that's infinity. So ibig sabihin, nagkaroon tayo ng current dito, a momentary current, you call it an impulse current that went all the way up to infinity. Is that possible? Question, is that possible? Can I have an infinite current that flows momentarily? In reality, it's impossible. It's impossible. Okay? It's impossible for an infinite current to flow. And that's why we say the voltage cannot change instantaneously. Yan yung rason na sinasabi natin to. Your voltage cannot change instantaneously. And the same thing for your inductance. Your current cannot change instantaneously. Okay, there are instances where you think the voltage changes instantaneously, but actually it does not. No, there's a finite amount of time, but maybe a very short amount of time. Okay, the other thing about capacitor is if the voltage is constant, the current is 0. Your capacitor acts like an open circuit to DC. For an inductor, if the current is constant, the voltage is 0. So your inductor acts like a short circuit to DC. And it's easy to imagine this. Bakit open circuit yung capacitor? Kasi insulator lang siya, di ba? If you imagine your two plates, there's an insulator in the middle. At steady state, we say at steady state, current cannot flow through your insulator, so it's an open circuit. On the other hand, bakit short circuit yung inductor? Kasi ang inductor mo, wire lang naman yan eh. Wire. If it is a perfect wire, it's a short circuit. It's a short circuit. So it's easy to imagine why your capacitor acts like an open circuit to DC and why it acts like a short circuit to, why your inductor acts like a short circuit to DC. And that's why when we study DC circuits, that's why we didn't study capacitors and inductors. At least in steady state analysis, no? Tinatawag nating steady state analysis. You're going to be studying transients, I guess, next semester, no? Next school year, maybe. Transients. This is when you first put a circuit together, before it reaches steady state, there are transient conditions that will happen. Okay, pag-aaralan nyo yun, no? But in our analysis, in our DC circuit analysis, first part of the semester, We just assumed steady state. Hindi pa natin kino-consider yung transients. And why did not we study capacitors and inductors? Because in a DC circuit, under steady state, your capacitor is really just an open circuit. And your inductor is really just a short circuit. That's why we did not have to study it sa DC. That's why all you studied earlier was just resistive networks. Pero magbabago yan, AC. That's going to change now. Okay, because if you have time changing voltages, so if your voltage is not constant, if it's time changing, your current through the capacitor is no longer zero. No? Or if you have time changing currents, your voltage across your inductor is no longer zero. Okay? Again, no? When you say current through the capacitor, don't imagine charges flowing through your dielectric, because charges will not flow through your dielectric. Okay? What happens is you're just displacing charges. You're displacing charges on your positive and your negative uh, plates. Okay, capacitor combinations. So this is very easy for you to derive. If you have capacitors in series, your capacitors in series, 1 over the equivalent capacitance is equal to the summation of 1 over each individual capacitance. No? 1 over CEQ is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. So this looks like resistors in parallel, di ba? Okay. And then capacitors in parallel, your equivalent capacitance is just the sum of your individual capacitors when you have capacitances in parallel. No? And I leave the derivation up to you. You should be able to derive this, okay, from the voltage current relationship of your capacitor. No? You should be able to derive this from I is equal to C dV dt. Okay, this is all the same I. No? And so you add the individual voltages. Okay, so you you add the individual voltages, which are actually integrals. No? So you have 1 over C1, the integral of I dt, 1 over C2, the integral of I dt, and dun lumalabas yung 1 over C equivalent is 1 over C1 plus 1 over C2 and the like. Dito naman, your voltages are all the same, and then your currents are the sum of all the currents in your capacitances. No? So you have I1, I2, I3. So I1 is equal to to C1 dV dt plus I2 is C2 dV dt and so forth. You're going to come up with an expression for C equivalent. Inductors naman, inductors in series, okay, you just add all the inductances. Inductors in parallel, it's parang resistors in parallel. Okay, that's not the only material I have for today, no? But before I move to the next material, any questions with regard to this? Any questions with regard to inductors and capacitors? Wala. Okay, so let me move on. No? Okay, so remember this is all a segue into AC circuit analysis. AC circuits, our excitation or our sources are sinusoids. No? Sinusoids, these are sine or cosine functions. So all the voltages or all the currents in our circuits will be either sine or cosine functions. So what I'm going to introduce now are sinusoids, the concept of effective value, and then resistance, inductance, and capacitance with sinusoidal excitation. Okay, the sinusoidal function. Why are we so interested in sinusoids? Because this is the natural output of an electric generator. An electric generator, you have a coil in a fixed magnetic field. You turn the coil around. No? Because of the circular motion of your winding, okay, the output voltage ends up being naturally sinusoidal. No, that's related to the circular motion of the shaft of a generator. Okay. In describing sinusoids in electrical engineering, most of the time we use the cosine function. You have an option; you can use the sine function, but in the convention that we have adopted is the cosine function. I believe most books actually use the cosine function. So this is the time domain expression, or the time expression for a sinusoid, for a general sinusoid. F of t, it's a function of time. F of m cosine, and then you have omega t plus alpha, where f of m is your amplitude or your peak value. Omega is what we call your angular frequency, which is in radians per second. And alpha is what we call our phase angle. Okay, this is the phase angle at t equal to 0 in radians. I think that's easier for you to visualize. If I have this sinusoid, okay, this is my alpha, this is my phase angle at t equal to 0. Note that if alpha were equal to 0, okay, this should be my axis. No? My axis should be here, because the cosine function is maximum at t equal to 0. Okay, but because we have a phase angle alpha, okay, my sinusoid is actually ahead of the usual sinusoid. No? At this point, it is already at angle alpha. No? Whereas if alpha were equal to 0, dapat nandito pa lang siya. T is what we call the period of our sinusoid. This is the time it takes to do one complete cycle. The frequency of the sinusoid is the reciprocal of the period. Frequency is equal to 1 over t. No? We call it, well, this is the period is in seconds, so frequency is supposed to be seconds to the minus 1. But we also say cycles per second. Cycles per second. And the common term for cycles per second is hertz. Okay. Omega is your angular frequency, no? So sinabi natin dito, omega is your angular frequency. The relationship between angular frequency and frequency is f, no? Is omega is equal to 2 pi f. Omega is equal to 2 pi times f. Why? Because each cycle consists of 2 pi radians. One cycle is 2 pi radians. No? This is, if you're measuring this in terms of radians, no? From this point all the way to that point, that is 2 pi. Okay? So I can express f of t in this manner. F of m cosine 2 pi ft plus alpha. Okay, the nominal household voltage in the Philippines is described by this voltage expression. V of t is equal to 311 cosine 377 t plus alpha. So yan yung mathematical expression ng voltahe na lumalabas sa outlet ng mga bahay sa Pilipinas. The peak value of the voltage is 311 volts. The angular frequency omega is 377 radians per second. Saan nanggagaling itong 377? Alam natin na yung frequency ng kuryente natin sa bahay is 60 Hz. So you multiply 60 by 2 pi, No? Omega is equal to 2 pi f, and you get 377. And if you compute for the period is 1 over f, you're going to get 16.67 milliseconds. In other words, for your electricity in your house to make one complete cycle, it takes 16.67 milliseconds. I remember the time when I was a student, mahal yung mga crystal. If you wanted to have a very cheap digital clock, no, what you would do is you would just divide the frequency of the Meralco by 60 to get 1 second. No? So that relied on Meralco delivering a frequency that is very, very accurate. Unfortunately, it's not the case. No? The error was very large. Pero ganun yung mga digital clock nun. No? Ginagamit lang yung frequency ng, at least yung mga mumurahing digital clock nun. Ginagamit lang yung frequency ng Meralco to determine what 1 second was. Okay, let's study the concept of leading and lagging sinusoids. No? So consider the plot of two sinusoidal functions, f1 of t, which has a phase angle of 60 degrees, and f2 of t, which has a phase angle of 30 degrees. Ito yung f1 of t. Okay? So at t equal to 0, meron tayong 60 degrees. No? So nauna na to by 60 degrees. Ano? And then this is f2 of t. At t equal to 0, 30 degrees pa lang tayo dito. Okay. We say that f1 leads f2 by 30 degrees. Ang f1 nauuna sa f2 by 30 degrees. That's the concept of leads. No? In other words, if you take a look at the two waveforms, if one of the waveform is leading the other, that means it is shifted left of the other. No? F1 is shifted left of F2. Yun yung lead. No? Or we also say F2 lags F1 by an angle of 30 degrees. Yun ang ibig sabihin ng leading and lagging. No? Okay. Effective value of a sinusoid. Yung IEFF is said to be the effective value of the sinusoidal current Is of t if it dissipates the same average power to a resistor R as Is of t. No? Again, no? try to digest that. I effective is said to be the effective value of the sinusoidal current Is of t if it dissipates the same average power to a resistor R as Is of t. No? Maybe I can illustrate it this way. No? So let's say I have a resistor R. Use a different color. No? Let's say I have a resistor R. No? The same resistor R here. Dito, ikakabit ko sa DC source. Dito, ikakabit ko sa AC source. No, let me not choose a source. No, current source dito. Current source. Sorry. Here I connect it to a. Ulit, no? So let's say I have a resistor here, R. Here I connect this to a current source, a DC current source. Same resistor R. And here I connect it to an AC current source. Okay, let's say this is IEFF. Okay, and then this is Is of t. Okay. So anong ibig sabihin ng effective value, no? If the average power delivered by Is of t to R is the same power delivered by IEFF to R, no? Remember that this is the same R, ha? Itong R na to, tsaka itong R na to pareho. Then IEFF is the effective value of I of t. Yun ang ibig sabihin ng effective value. If the average power delivered by this to R is the same power delivered by this to the same R, then this is the effective value of this. So you can think of effective value as like the equivalent DC value of a sinusoidal source, no? Equivalent DC value of a sinusoidal source. Okay, so if IEFF is the effective value, no, this IEFF will deliver to a resistor R this amount of power. No? R times IEFF squared. No? Power is equal to I squared times R. So R times IEFF squared. Now, if I have this sinusoidal current, I of t, sabihin na lang natin muna na yung alpha, yung phase angle is equal to 0. No? Because whether or not you have a phase angle, the solution will, or the results will be the same. No? So let's say this is my sinusoidal current, I of t. What is the power that will be delivered by that I of t to a resistor R? P is equal to I squared R. So P will be equal to R times I of t squared. So it's going to be equal to this, no? R Im squared cosine squared omega t. Because I is equal to Im cosine omega t. Now, what is the average value of the power? So this is a function of time. This is a function of time, no? In fact, what will this look like? Ano magiging itsura nito, no? Let's try to plot that piece of t. Okay? It's going to be I squared, no? So if originally this was my I, no? Remember, let's say this was my I. Ang magiging itsura ng I squared ganito. No? So this is what R Im squared cosine squared omega t will look like. That is what that will look like. Now, what is the average power? How do I get the average power? You might imagine average power this way, no? Kung ito lupa ayan, kukuha ako ng bulldozer, ibubulldoze ko to para maging patag siya. Yung magiging level na patag siya, yun yung average power. In other words, my average power would be somewhere here. Average power. Again, no? Imagine na ipapatag mo to, lupa yan, ipapatag mo, this level that it will come out to, that is your average power. Now, mathematically, okay, sorry, I have to erase this. Mathematically, we can determine that, no? Sorry, nagloloko uli yung PowerPoint. Yun, okay. Mathematically, we can determine that. No, why? Because cosine squared omega t, you have a trigonometric identity. This is 1 plus cosine 2 omega t all over 2. So actually, your power expression is equivalent to this, and the average of this average of this term is 0. No? Because the average of a cosine function is 0. Pag tinignan mo yung cosine function, ang average niya 0. Right? So yung average natin is just r im squared over 2. If I equate that now to r, I effective squared, remember, no? I effective, the power that I effective delivers to a resistor R is I effective squared times R. If I equate that now to this, what I'm going to get is I effective is I of m over the square root of 2. So this is the effective value of my current. If this were a voltage, V effective, so pwede rin yan sa voltage, no? So for voltage, V effective is equal to V of m over the square root of 2. No? So yun, no? Ito pala, nakasulat dito, no? So V effective is the DC voltage that will dissipate the same average power as V of t to a resistor R. So again, you might think of V effective as the equivalent DC value of an AC voltage with respect to the power it delivers to a resistor R. The effective value of a, something got lost here. Let me, this is an integral. The effective value of a periodic function is also called its root mean square value, or RMS value. That is, for a given periodic function, we can get effective value, which is equal to the RMS value. That is the square root of 1 over the period multiplied by the area under the curve of the square of the function over one period. So you square the function, okay? You square the function, you get the area over one period, you divide it by the period, and then you get the square root. That's why you call it root mean square. No? It is the square root, okay, of the mean is average, of the square. No? So if you take a look at this, if you take a look at this expression inside, this is the average of the square. Which is exactly what I was describing earlier. Yung sinasabi ko kanina, no? Yung waveform na pinakita ko na ng current. Okay? Pag pinatag mo yan, no, yung lupa, I made an analogy to Earth. Pag pinatag mo yung lupa, what are you doing? No? You're just getting the area under the curve and dividing it by the period. That's equivalent to, yun yung parang pinatag mo, no? And then you get the square root. That's why you call it root mean squared. I don't know why my... Okay. May nawawala sa slides ko sa iPad ko, no? Sorry. Now, the nominal voltage in the Philippines is a sinusoid described by V of t is equal to 311 cosine 377 t plus alpha volts. No, I already told you this earlier. Saan nanggaling ito mga numeron to, no? The effective value of this voltage is 311 divided by square root of 2, which is 0.707 times 311, yun yung 220. So that's why when we specify the voltage that comes out of our outlet, that is actually the effective value. That is not the amplitude. So ang 220 volts ng Meralco, actually, ang peak value nun is 311 volts. So pag nakuryente kayo ng 220 volts, actually yung pinakamataas na voltahe na naramdaman ng katawan nyo is actually 311 volts. Hindi lang 220 volts. So imagine that. Okay. Okay. Talking about sinusoids, resistors, and sinusoids. No? So consider a resistor. So this is the convention for voltage across and current through your resistor. And let's assume that this is the current flowing through your resistor. From Ohm's law, we know that V is equal to IR. So computing for IR, you just get this expression for V. So if this is my current, no, my voltage will just be my current multiplied by R. Okay, and notice that my voltage and my current, we say, are in phase. These are in phase. Pag sinabi nating in phase, walang nauuna sa kanilang dalawa. The voltage does not lead the current, or the current does not lead the voltage. They are in phase. Okay. Now what about your inductor? Let's say ito yung expression natin for yung current through the inductor. So this is just again an AC current. So this is our convention for voltage across and current through your inductor. Ano expression natin for V? Can you recall for an inductor? Can someone just shout it out? Ano yung V? V's of L? Anyone? Nakalimutan niyo? Is equal to
LD.
L di
Okay.
by dt. Right? L di dt. So if I get VL equal to L di dt, this is going to be my expression for V. No? It's going to be, L multiplied by the derivative of I with respect to t. The derivative of I with respect to t is going to be negative omega, because the derivative of cosine is minus sine. Negative omega, the derivative of cosine, so negative omega I of m sine omega t. And if I plot this, kung ito yung IR ko, ito yung magiging VL ko. So now you see that the voltage, okay, the voltage across your inductor is not in phase with the current through your inductor. Okay? Ang nauuna yung voltage. Nauuna yung voltage, no? Remember I said, no? If yung nauuna, parang nasi-shift to the left. So nauuna yung voltage, tapos saka yung current, no? So the current lags the voltage by 90 degrees. If you take a look, the difference between the zero crossing here and the zero crossing there, that's 270 minus 180, that is 90 degrees. And if you consider your capacitor, again, let's say this is your current through your capacitor, it's a sinusoid. Ano yung voltage across your capacitor? It's an integral, no? The voltage across your capacitor is 1 over C, the integral of I dt. Okay, if I just integrated this, no, let's just assume that this is an indefinite integral. So just integrating this, I'm going to get this expression for V's of C. No, the integral of cosine is sine, and since there's an omega, we have 1 over omega. And if I do the plot, ito ngayon yung I's of C, and notice, dito ngayon, siya nauuna. Nauna yung I's of C, saka dumadating yung V's of C. So we say that the current leads the voltage by 90 degrees. So in an inductor, the current lags the voltage by 90 degrees. In a capacitor, the current leads the voltage by 90 degrees. Okay, so if you have an AC current flowing through your capacitor, again, flowing through, you don't really have a current that is penetrating the dielectric, no? What happens is yung charges mo sa capacitor, yung charges mo pag ganyan-ganyan, no? It's displacing in a sinusoidal manner, no? And so you have that's how your current is flowing. But from the point of view of circuit analysis, it almost looks like the current is flowing through your capacitor, no? So the current leads the voltage by 90 degrees. So this is your summary. In a resistor, IR and VR are in phase, and an inductor, IL lags VL by 90 degrees. In a capacitor, IC leads VC by 90 degrees. Okay. And later on, you're going to see that when you have a resistor and inductor in series, the current will be between 0 and 90 degrees, the current lagging. When you have a resistor and capacitor in series, the current will be leading. It will be between 0 and 90 degrees. And when you have a resistor, capacitor, and inductor in series, it depends now on the relative values of your resistor and your capacitor. But that's getting ahead of the lesson. Okay. Actually, this is not the presentation I wanted to show, but okay, circuits with sinusoidal sources. No? So let's consider this particular circuit. This is a very simple RL circuit. We say an RL circuit is a resistor inductor circuit excited by a voltage source, V of t. Let's say the voltage source is sinusoidal. So V of t is V of m cosine omega t, where V of m and omega are constant. V of m and omega are constant. And let's say I, we want to compute for the steady state current that will flow. We want to compute for this I. Now from KVL, we know that the voltage, this voltage is equal to the voltage across your resistance plus the voltage across your inductance. Again, this voltage by KVL is the voltage here plus the voltage here. Now the voltage across your resistance is just your R times your I. The voltage across your inductance is L multiplied by DI by dt. If I add these two terms, that should be equal to my source, which is Vm cosine omega t. Now you should be able to solve this if you know how to solve differential equations. This is what you call a first order differential equation, a first order non-homogeneous differential equations. Nag-differential equations na ba kayo sa math? I just want to know. Did you take up differential equations in math? So dapat yung mga nakakuha na ng differential equation should be able to solve this, no? Okay, when you solve the differential equation, you're going to get your transient response. Or well, in math they call it your what do they call it? The kalimutan ko na yung term sa math, no? But there are two solutions you get. One is you make this first homogeneous, you make this equal to 0, and you get the natural, what we call the natural response in electrical engineering, no, which is also your transient response. And the other is you consider now your source, no, and you get what you call your forced response. I think the forced response in math is what they call the particular integral, no. Kalimutan ko na yung term sa math nung natural response, no. So you can solve this if you know how to solve differential equations, but it's not easy to solve differential equations, no? Especially when your circuit gets very complicated. This is only a one loop circuit, okay? And furthermore, we're not interested yet in the transient. We just want the steady state. No? Now in triple E, okay, we solve this problem in another way. No? We solve this problem, we say in the frequency domain. No, this is an alternative method of solving for the steady state response of linear circuits with sinusoidal excitation. It's going to require a transformation. That transformation is from the time domain to the frequency domain, because this is what we call a time domain expression. You have here the variable t. we're going to transform the circuit to what we call the frequency domain. Unfortunately, when we do that, you're going to have to deal with complex numbers. So you're going to have to review your complex algebra. I will no longer go through a review of complex algebra with you. No, there are a lot of, first of all, um, that should have been introduced to you even in high school, and then probably also in your earlier math courses. No, the idea of complex algebra. Just to say that sa electrical engineering, we don't use I as the square root of -1, but we use J. No? The reason why we use J instead of I is we don't want to confuse the square root of -1 to be a current. So ayaw natin gamitin yung J. No? So I'm going to stop here, but I'm going to advise you to review your complex algebra. No? So just to breeze through what you need to know. So you need to know what a complex number is. It has a real part and its imaginary part. You can express it in rectangular form, just like these numbers here. No? You can show it in the complex plane. So this is your Cartesian coordinate system where you have a real axis and you have an imaginary axis. And then you should be able to express your complex number also in polar form, no? Magnitude and angle. So if this is your complex number A, no, which is equal to small letter a plus jb, you should be able to express that as a magnitude. So this is your magnitude and your angle. No? Okay. Sorry, there's something wrong with the way my iPad is displaying my PowerPoint. No? So anyway, just review that, no? Just review that. And then when we meet again on Thursday, we're going to jump into um, what we call phasor analysis, which is frequency domain analysis. Are there any questions? So this part of the course, I'm warning you, is not trivial, no, because it's very conceptual, no. But once you get the hang of it, then it becomes quite easy. So it's just absorbing it in the beginning that's a little bit difficult. So you really have to give special attention to this part of the course. Now I know it's not easy at this point because you're also worried about your exam, you know. So that's why I also don't want to overload you too much at this point. Okay, are there any questions? No questions. Okay. I'll stick around until the last person logs off so that if anybody wants to ask questions, I can still entertain them. So that's all for today.